Now let us see the properties of a modulus of a complex number and some of the examples followed by that. Firstly, if mod of z is equal to 0, then it means the number itself must be 0. Secondly, the modulus of z, z bar, minus z and minus z bar is all same. In the third one, we have minus of mod z less than or equal to real part of z, which in turn is less than or equal to mod z. And if we just change real part with the imaginary part, still the same inequality holds. So in other words, the property 3 is saying that the real part as well as imaginary part of any complex number lies between minus mod z and plus mod z. Now this is very much evident from if we see the basic diagram of a complex number plotted on a complex plane. We know that this is the real part of the complex number and this is the imaginary part of the complex number, and the modulus is nothing but this line joining the origin and the complex number z. So as this forms a right angle triangle, and as we know that the two perpendicular sides, each of those perpendicular sides is always less than the hypotenuse, therefore it follows from this the third property. Now the fourth one, which we have already seen in the conjugate also, that is the product of z and z bar is equal to mod z the whole square. The fifth and sixth property are also on the same lines as we saw for the conjugate, that is here the modulus of z1 into z2 is nothing but modulus of z1 into modulus of z2, and for division also mod of z1 upon z2 is equal to mod z1 upon mod z2, provided z2 is not equal to 0. Now let's see few more properties. Now here we have a very important what is called as triangle inequalities related to two complex numbers. It directly follows from the property of a triangle which we all know, that is, any one of the sides is always less than or equal to sum of the other two sides. Now the equality will hold only when all the three vertices are collinear, so that is not really a triangle as such, but in general it will be less than or equal to. Now same applies for the complex numbers also, that is if we have say z1 as one of the sides of a triangle and z2 as another side, and by the addition law, like this goes very much tangential with the vectors. So if we add z1 and z2 considering those numbers as vectors, then we get z1 plus z2 as the third side, and hence we know that the magnitude of z1 plus z2, that is nothing but the length of this particular side, has to be less than or equal to magnitude of z1 and z2. So here it is wrongly written as z2 bar, it is nothing but simply z2. So mod of z2 is the second side, so therefore it proves the first triangle inequality. Now z1 plus z2 is greater than or equal to modulus of mod of z1 minus mod of z2. So here also it follows from the vector addition or the triangle law that mod of z1 plus z2 is greater than this particular quantity on right hand side. Now similar to addition of two complex numbers and taking the mod thereafter, we have the subtraction of two complex numbers, that is z1 minus z2, and then taking the modulus, and right hand side remains the same as the above. So these are the four important triangle inequalities. Now if we want, we can look at these from another way also, that is, if we think of the first two, we have mod of z1 plus z2. Now since it is less than or equal to mod z1 plus mod z2, so we say that the maximum possible value of mod of z1 plus z2 is nothing but the right hand side, that is mod z1 plus mod z2. On the other hand, if we incorporate the second property here, we can say that it has to be greater than or equal to mod of mod z1 minus mod z2. So this is the least possible value of mod of z1 plus z2. So similarly, we can also write the corresponding inequality for the other case also. Now let's move ahead and see few more properties. Now here it's a kind of square relation, that is square of mod of z1 plus or minus z2 is given by mod of z1 square plus mod of z2 square plus or minus 2 times real part of z1 into z2 bar. And we know that z1 into z2 bar's real part is same as the real part of z1 bar into z2. Now the ninth property is again evident, that is, if we have mod of z1 plus z2 the whole square plus mod of z1 minus z2 the whole square, then the middle term will get cancelled and we'll be left with 2 times mod of z1 square plus z2 square. And lastly, we have modulus of nth power of z is equal to the nth power of the modulus of z. So these two operations are commutative. Now let us move ahead and see a couple of examples based on the properties of modulus. Now here we have to evaluate the modulus of this particular expression given. Now the mechanical way is to actually calculate the shortest expression inside the modulus and then take the modulus. But instead of that, we can use a simple trick, or rather nothing but the property of modulus, that this particular expression is nothing but modulus of 1 plus I into modulus of 2 plus I divided by modulus of 3 plus I, which follows directly from the property of modulus. Now here we know that modulus of 1 plus I is 1 square plus 1 square, which is 1 plus 1, into modulus of 2 plus I is 2 plus square is 4 and plus 1, and divided by modulus of 3 plus I is 3 square is 9 plus 1 square is 1. So we have root 2 into root 5 upon root 10. And we know that numerator root 2 into root 5 is root 10. So that gives us the final answer as 1. Let's see another question. For any complex number z, the maximum value of mod z minus mod of z minus 1 is equal to how much? Now if we recollect the triangle inequality, one of the triangle inequality was mod of z1 minus z2 is always greater than or equal to mod of z1 minus mod of z2. So if we just rewrite this, we can say that mod of z1 minus mod of z2 should be less than or equal to mod of z1 minus z2. So we are just interchanging the two sides of the inequality. So in other words, it means the maximum value of this particular left hand side is equal to this. So maximum value of mod of z1 minus mod of z2 is mod of z1 minus z2. So therefore, if you want to know the maximum value of the given expression, that is mod of z minus mod of z minus 1, that should be equal to mod of z minus the other number, that is z minus 1, which is nothing but z will get cancelled and you will have simply 1, and modulus of 1 is nothing but just 1. So therefore that's the answer of this question. Let's go to the next question. Now here is given that if z is equal to x plus iy and iz square minus z bar is equal to 0, then find the value of modulus of z. Now z is equal to x plus iy just means that z is a complex number. So let us start off with the given condition that iz square minus z bar is equal to 0, which means we have iz square is equal to z bar. Now since we have to find the modulus, that means somewhere we must bring in the operation of taking modulus. So let's take the modulus of both sides and let's see what happens. So taking the modulus, we have this step. Now breaking the modulus, we have mod of I into mod of z square is equal to, now mod of z bar I can write as mod of z because we know from the property of modulus. Now here modulus of I is nothing but 1, and therefore what remains is modulus of z square. Now again using the property of modulus, we can write this as modulus of z the whole square is equal to modulus of z. So now therefore if we bring the mod z on left side, we have mod z the whole square minus mod z equal to 0. So taking mod z common, we have mod z minus 1 is equal to 0. So that implies mod z is either 0 or the bracket is equal to 0. That means mod z has to be equal to 1. So there are two probable values of mod z, which is either 0 or 1.